Hello guys, in this video I'm going to go over another example in solving RLC circuits, particularly when you have an impulse signal. So the first thing, as with on every other circuits, is to come up with some kind of equation. So we use KCL, as with other examples, on this node. And the equation can be written in this form. Since the current coming out of this node has to be equal to 0, we can write this equation. And using the previous equations that describe the voltage and current relationship in inductors and capacitors, we can rewrite this equation in this way. And just to let you know, this u of t refers to a step function. And a unit step function is a function that has 0 value before time t0 and a value of 1 after t0. So this 6 times u of t would look like this function. And since we are only interested in what happens after this signal is applied, because obviously before the signal is applied, everything is going to be 0. So to get our second order differential equation, we are going to differentiate both sides. Then we assume v of t to be some form of k times e to the st. So if we replace v of t with k of e to the st, we can rewrite this equation in this way. If we put k times e to the st to the left side of the equation, we get this equation, which is called the characteristic equation. And this characteristic equation is equal to this equation, and this equation has the discriminant which is equal to 0. So this equation only has one root. And since s in this case is equal to 2, our alpha is also equal to 2. So out of these three cases, we need to use this equation. The next thing we need to do is to find the value of k1 and k2. In order for us to do that, we need to know two initial values. The first one is v of 0, and the next one is v prime of 0. And since we are only interested in what happens after the signal is given, we're going to add a little plus sign next to our zeros, which refers to the point just after time t0. And in the case of capacitors, we know that the voltage across capacitors cannot change instantly. So this v of 0 plus is also equal to v of 0 minus, and this 0 minus refers to the point just before the signal is given. And of course, we know that this is 0, because if there is no signal given, there will be no energy present in this circuit, and the whole thing would be equal to 0. To find the value of v prime of 0, we need to plug 0 to this equation. If we do that, this part is erased, and we are only left with this equation. And we know that v of 0 is equal to 0, so our v prime of 0 would equal to 48 in our case. And of course, this is 0. Finally, we can find the value of k1 and k2 using these two values. If we plug 0 to this equation, this whole equation becomes k1, because this part would be 0. If we differentiate this equation, we get this equation. And if we plug 0 to this equation, this part is erased, and we are left with minus alpha times k1 plus k2. And we know that this alpha, in our case, is equal to 2. And this, in our case, would equal to 48. And since k1 is 0 in our case, k2 is 48. And the final answer is this. Another way to solve this problem is using the Laplace transform, and things get much easier in that case. For inductance, we change L to S times L, and for capacitance, we change it to 1 over S times C. So in our case, 2 Henry would become 2 times S, and 1 over 8 would become 8 over S. Then we treat these components as having the resistance of this value, and we solve the KCL equation. Now this is only possible because we do not have any initial energy stored in these components that is unrelated to our source. If an initial condition is given, if there's initial energy stored in here that is not from this source, then we would need to add these components. And I'm not going to go over where these two components came from because we covered it in our last video. So, if we write the KCL equation in Laplace domain, the equation that we get is this. Now I found the Laplace transform of u of t using the Laplace transform table. This would equal to 1 over s in the Laplace domain. So if we organize this equation and try to find the value of v of s, the equation that we get is this. And this, using the inverse Laplace transform, in time domain, this would equal to our original answer. Here we have seen how simpler everything has just become. So I strongly suggest you use the Laplace transform when solving RLC circuits. And I strongly suggest that you memorize some of the important Laplace transform table. Because once you get used to it, it's not that hard to memorize and it will help you in so many ways.